you have to share that with the whole group. Francesco.
Oh, of course.
Don't open the wine in here.
Not in here.
No, that's
Yeah.
right. The firemen don't like that. Okay, well, I'm excited to have Francesco come again and talk to us. I'm starting to realize Francesco's my go-to guy for techie glider problems. And he just was casually commenting about a way to measure battery resistance. And it really captured my imagination because batteries, I mean, anyone who's been in our hobby, especially guys who I came up through kind of motor glider rigs, with a foamy motor glider to teach myself to fly. And back then the nickel cadmium batteries were 600 milliamp hours, very small batteries, and you had to like charge them, and we had wall wart to charge them, and it was kind of it just seemed like it was half the hobby was taking care and feeding of your batteries. And then of course we all switched to lipos or nickel metal hydrides and then lipos. And it's got a lot easier. The early days of lipos, it was actually kind of scary when you had all these videos of people burning down houses, and it still is, but we don't really talk about it. And so I thought this whole area of batteries is just something we all should know about. Yeah, I have my stack over there. We should all be talking about and learning more about. So we have an amateur scientist actually doing some research with battery stuff that we could perhaps learn from. So Francesco, we're just really happy to have you. Thank you. Let's go.
Yeah, so the idea started from a small device that I built, and I found that it's mainly uses for in our modeling business. So maybe if we can you guys go next slide, please? Okay, so of course we all know this. Ideal battery is drawn in circuit schematic is a pure voltage generator, but any real battery can be seen as an ideal battery with a series resistor next to it. And what we measure at the battery terminals is the result of this series circuit between the ideal battery and the real internal resistance. So next slide. Why should we care? Well, because the net effect is what we observe as the battery terminals. So it means that the voltage that we measure depends on the load, depends on how many amps we draw. And typically what happens is exactly what we don't want. As the load increases, at the moment that we need our batteries more, the voltage drops because there are ohmic losses across the internal resistor. Next slide. This is a real data logging from actually an F3D winch launch. So the red curve, which is red here, is the ampere ohm, and the blue curve is the voltage at the battery terminal. Actually, when entering the receiver, so past the switch, past all the connectors. Now, if we zoom in the moment, this is the zoom. So you see that this is the altitude. The model climbs, then you dive down and zoom. And the moment, not surprisingly, the moment that you zoom is where you record the highest ampere ohm, because you are forcing all of your wing servos to work to produce camber and to get the model to change the direction and it's pointing to and the zoom out.
Is this on the model or is this the winch battery?
On the model, sorry. It means that now we're going to zoom in, but it's almost 3 amps from the battery of the model to the receiver, actually to the servos through the receiver. So
The purple line is the actual flight path of the glider.
it's actually the altitude.
The altitude of the glider.
Yeah, so everything is in German because the software is in German, but yeah, height, voltage, current. And it's in meters, it's German. So if we go to the next slide, we have a zoom from where we can read, actually, that the maximum current was a little bit over 2.8 amps, and the voltage dropped from 5.15 volts to about 4.65. So if you do the math, you have a 0.5 volts drop at 2.8 amps, which means 0.18 ohms. That's the internal resistance of the pack, which not surprisingly, is one of the packs that we all know. It's a it's no longer NiCad, it is a nickel metal hydride cells. These are 4 N groups in series. So 180 milliohms from a 4-cell pack. But this is still a healthy pack, but what if the drop were larger? I'm sure that we all heard horror stories of people who launch and that they lose radio control immediately after zooming and the plane crashes. Well, this happened especially in the very early days of 2.4 gigahertz radios, in which were some radios, famously some spectrum models and also some Fratado models, that would run out when the voltage went below 3.5 volts. And it's not that far because it's already we are 4.6 volts in this case. This was a fully charged battery. If you have if you already flew a few rounds, you may be at risk. So we want to avoid this. Next slide. And how do we avoid this? How do we model this? Well, first of all, we have to imagine, we try to figure out what are the possible sources of losses in our model. And let's focus for the moment on a TD plane. So we have a 4-element battery. We have some connector that takes you to a switch. So servo connector between the battery and the servo. Then you have a switch, and then you have another connector going to the receiver. So each of these elements has some parasitic resistance. So next slide, we see the first one. These are specs from Molex for a connector which is very similar to our servo connectors. Contact resistance, 15 milliohms. And in our batteries, we have one to go and one to come back. Then we have another source, the switch. Next slide. CNK switches, this is the one that I normally use. I like to use this because they are sealed, unlike most switches that you can buy from hobby shops. So I don't have to worry about the humidity getting seeping inside. Contact resistance, below 10 milliohms, typical initial. They don't even bother to declare how much after 10,000 switches, but we can assume that maybe doubles or triples. So it's another source of resistance that we can roughly compare to the one that we get from the connectors. Not surprising, it's a connector that is actually actuated with slide. Third, we have the wires themselves. Next slide. So this is a table from Wikipedia. If we use a gauge 20, it's about 10 milliohms. Am I reading it right? Yes, 10 million per foot. So we probably don't have 1 foot of wiring between the battery and the receiver, but maybe half. So it's another 5 milliohms. Or if we like to use very lightweight wiring looms, like they deliver with Explorers or Maxa planes, they are AWG24. It's significantly higher. So we need to take all this into account. So summing up everything, next slide. Oh, sorry, I forgot the battery itself. This is what Sanyo says about the N-loop batteries. It says approximately 25 milliohms, but they actually measure it with an AC measurement technique. So it's basically they pulse a load 1,000 times per second, and they measure the voltage change. So let's assume that if this is a realistic figure, so it's 25, 4 cells, 100, and then we have to add the switch, and we have to add the wire, and we have to add the connector. So in total, next slide, we can expect between 130 and 140 milliohms. But what's also worth noting is that the battery internal resistance increases as the battery ages, because the chemistry is not, it's a chemical reaction, so it tends to get not exactly the same performance as new when the battery ages out.
Francesco,
Yeah.
on that, I've noticed something with nickel metal hydrides, because I have the feedback on my transmitter, so I can watch the voltage.
Oh yeah.
When I first, even with a fresh battery with a full charge, when I first turn the radio on, let's say I get 5.6 volts or so. When I'm rapidly losing move the sticks back and forth, I'll see the voltage drop a good half a volt or so.
Yep.
But then, after I moved it, for a second or so, it stabilizes
recovers.
back to that original voltage and it stays there.
Which is good, but it takes a while, right?
It takes
It's
a
not, yeah. This is why a measurement with a very fast pulsating load, like 1 kilohertz pulse load, is not the best measurement technique, because you are actually measuring the fast reaction of the internal chemistry and not what really interests us, which is how long will it take to recover, for instance, after you zoom. Will you have control back by the time you have to stabilize into horizontal?
It also
flight?
brings it into question, if you just take the plane, turn it on, you don't move this surfaces much, you zoom, you hit the zoom, now it's gonna, the voltage is going to drop
Yep.
when you hit the zoom.
Exactly.
Even with a fresh battery.
And also, if you don't touch anything, I don't have a telemetry receiver, I have an onboard voltage meter.
Yes.
If you don't wiggle your servos, your voltage meter will always, 100% of the time, say, oh, the battery is perfect. But if you start doing that, you start noticing that it's not exactly like that.
That's how I catch a bad battery.
Same here. Yep. So, if we assume that you remember the pack that we discussed in the initial slide, 180 milliohms caused about half a volt drop. Well, if we wait long enough and we let the battery resistance double, we may be looking at 1 volt drop. That's probably too much. You probably wanted to dump the pack by then. But we have to understand, to be able to tell when the time is right to replace the pack. So, the next slide. It's even worse for FIJ and ALES, but because this requires a LiPo packs, because we want a high discharge capacity, so high C, to the C figure that all the manufacturers advertise. We can expect an amp drop anywhere from 30 to up to 100 amps. And of course, if we were doing F5B, these figures would be incredibly small because they go 400 amps. So what is interesting is that the effective energy, so current times voltage that can be extracted, is actually limited by the internal resistance, because voltage drop under load means that lower power is available for a given amp drop. And if you use an electronic speed controller, it's actually the cutoff voltage built in or programmed in the ESC that sets your upper resistance limit. If your resistance is so high that when you give full throttle, the voltage drops below the ESC after the threshold, you're not going to fly. Next slide. So, ideally, we should measure, just like I did in the first slide, with either with telemetry or data logging, we should be able to measure the series resistance of the whole power supply chain, be it TD or FIJ. But maybe you don't have a telemetry system like I had, or maybe you don't have a data logger, but even if you have it, it takes time. You need to download your data, do some math. So it requires a specialized equipment and requires some time to be spent on that. But if we assume that the wires, the connectors, and the switch typically tend to age better than the battery pack itself, because it's just mechanical parts, there's no chemistry involved, we can probably shift our focus onto the pack and periodically check the internal resistance of the pack and forget about anything else. You can just check everything else periodically, but without not with the same level of attention that the battery deserves. Next slide. So I came up with this idea. Let's build a handheld device that you can put in your flight box and the field box and check before flying, check it anytime you want. To measure what? To measure the battery's equivalent service resistance. The way this works is by measuring the voltage recovery, exactly what you were referring to, Rob, at the battery terminals when a calibrated load is disconnected from the battery. So we do exactly that. We put the battery under load, then we disconnect the load and measure the recovery. From there, of course, we calculate the series resistance using Ohm's law, and we directly display it on an LCD. Next slide. So I made everything open hardware, so everything is available. This is the schematic. It's a microprocessor controlled. This is an Atmel 80 mega 328E microcontroller. This is just a serial port. This is just a connector for the LCD. This is the active part. So there is a current source implemented with an LM317, which is switched on and off with this MOSFET. There's a current sensing resistor, 1% precision. And of course this draws amps from the battery. Also the battery is connected to those with a 4-wire technique, the Kelvin technique. It's connected to 2 sense wires, which are AC coupled to 2 of the analog to digital converters of the micro, so that the micro can read at the same time the voltage drop, and the current, which is sensed through these 2 lines. Next slide. I also designed the board for that. Simple through-hole 2-side PCB, and I actually have some images here. This is it. Next slide. It is also here. And if one populates the board with all the components, next slide, it's a relatively compact installation. You just need to put a micro that you have to program with the software that I wrote for this. One port, one crystal, a couple of capacitors. This is the sensing network is here, and that's the load, the variable load with the heatsink, and the LCD module is the absolutely standard one. The only perk is that it's a 3.3 volt instead of the more common 5 volts, so that it can be used also with a 4-element NiCad battery, so without having to worry about the voltage drop of the voltage regulator. Next slide. So this is the assembled unit, and I'm going to pass it around so everybody can see it. And I absolutely encourage anybody who is interested in this to download all the design files and build your own. It's very simple. There's no SMD required. Everything is through hole. If you can solder, you can build it. Next one. This is the way it works. So if you assume that this is the battery under test, this is the load that can be switched on and off by the micro. The way it works is by sensing the voltage at the battery terminals. So I wanted to be able to measure up to a 5S LiPo cell, which means what is that, 17.5 volts or something like that. So it's typically more than what I can put in the analog to digital controller ports on the micro. So instead of measuring it in DC, I measure it in AC. So I pass the voltage through 2 capacitors, actually two RC filters, and what I measure is not the drop itself, but it's the spikes that come after the load is inserted and then removed. And of course, the micro is fast enough to measure this before it drops. So it's a very, very quick measurement. And the load is not always on, as a 25% duty cycle. So I take the load on for 500 milliseconds and off for 1500 milliseconds, so that even the heat dissipation in the LM317 is not high, even with the 5S or probably even with the 6S LiPo. So it actually works without getting too hot. Next one. I also confirmed with an oscilloscope that actually what you see, so the yellow trace, you see 4.8 volt, is the actual voltage measured at the battery in DC. And the green trace is the voltage in the sense line. So this is referred to not to 4.7 volts, but actually to 43 millivolts. So as you can see, the scale is the same for the 2 traces, 1.1 volts per, 1.1 volts per division. You can see that the 50 millivolts per division in both cases, you can see that the magnitude of the drop, actually of the recovery, is exactly the same that I measured on the AC line. Next one. So, doesn't require external power, it's powered directly by the battery under test. Works anywhere from 4.8 volts. Actually, you can even measure a single LiPo cell, so it's less than 4.8, it's actually 4, up to a LiPo 5S. There's nothing that prevents it from having more than 5S, but the heat dissipation may become more important, so you need to be careful maybe with a bigger heat sink or putting in a small fan. Uses a Kelvin type measurement, so with the 4 wires, 2 wires are actually power wires and the other ones are just sense. So there's no way to discount any drop on the wires. You can measure the pack resistance or even the individual cell resistance. This is mostly useful for LiPo cells because LiPos have the voltage tap for individual cells. It's not an ohm meter. It needs to have a voltage source connected to it. But if you work by difference, you can measure the difference between the resistance measured at this pack and the resistance measured after switch. And so by difference, by subtraction, you can get the resistance of the switch harness itself. And it's microprocessor controlled. It's an Atmel 328P with Arduino bootloaders. It can be programmed very easily, and so software can be enhanced as one likes. Next slide. And I make everything available on GitHub. So design files and the firmware. And I strongly encourage doing it yourself. The PCBs that you have seen, those are made by a service in Oregon, actually. So they are actually made in the US. And you get 3 of them, because the minimum lot is 3 pieces, for $22. So it's not particularly expensive.
But you need 2 PCBs, right?
You need just 1.
Oh,
But the minimum production lot is 3.
well, but I thought there was a black one and a red one.
Oh, the red one is actually is the LCD module, which is an industry standard module.
See, that's off the shelf.
You can buy it off the
Yeah.
shelf. Yes. The only peculiarity is that it's a 3.3 volts instead of 5. But nowadays it's easy to find. And yeah, the service that I use it's called Oshpack, and it's really good quality. If you have the board, you can see that all the holes are perfectly plated and that they are perfectly centered in their pads. Quality is good, no short.
So are you or are you not applying the load?
I am. The load is about
What's the load?
800 milliamps.
How does that differ than like Wayne Giles' ESR meter in the UK? Is this similar?
I think he uses a stronger load for a shorter time.
It's same, but similar.
It's a similar technique, yes.
Same principle. Yeah,
Same
if you're familiar with
Oh,
that
yeah,
one.
yeah.
That's
Well,
really
there
cool.
are not many ways to measure.
It's what?
There are not so many ways to measure in terms of
Yeah.
resistance. We all use the DVDI method.
I noticed on my chargers, most of them do have an ESR built in.
Yeah.
Are those just not as accurate or?
So I don't know about yours. Mine measures senses the voltage through the same wires that it delivers current to the battery with. And so you have to account for
For
the
your
resistance of the wires themselves.
Right.
In this unit, these are the power wires, these two.
Yeah.
And it's nice 16 AWG. And this is the sense wire. So if I measure directly on the battery tap,
Right.
I don't even need to account for the resistance of the connector because no current flows through.
Yeah.
Can we go to the next slide? And so it's very interesting and actually useful to gauge the health of the battery by comparing the individual cells reading. So if you have a LiPo battery balancer, you know that you can see if your battery is in good or bad shape by checking how out and off balance it is. You can do the same with internal resistance without needing to go to the long charge process. So I'm gonna demo that, and I have a 3S battery, you can tap into the individual cells and see how much difference there is. And when they start to become very unbalanced, you probably can expect that one of the cells is going to die soon. Unfortunately, the individual cell tapping is very common for lithium-based batteries, but I have never seen it for nickel batteries. We typically don't do that. And it's a shame because it would be interesting to see which one in the 4 cells in your pack is gonna die first. But if you make your own packs, nothing prevents you from tapping the individual voltages and putting it
I always
on.
do that when I have a pack that has failed. I always take it
Yeah.
apart and find out which one has
Yeah.
failed.
And with this kind of meter, you can do it without taking the pack apart, without using the voltmeter. Because we all know that the typical failure mode is that the weaker cell ages more quickly than the rest because it's subject to the same kind of load as the other, and is a very good indication of the health of the cell is comparing its internal resistance to the rest of the pack.
Do you use the balancing connectors to do that? Okay.
So I use the standard
JXT
9.1 pitch connector, and most batteries that have JST connectors have that. The notable exception is the old Thunder power packs that have a metric pitch. I think it's 1 millimeter instead of 1.27. Next one?
By the way, they changed that now.
Yeah, I guess so.
Yeah.
Because they want it to be more standard, and it seems a good idea.
So everything's gone JTF. That's become the standard connector now.
So, of course,
Okay.
we all know a good battery is of course made of good cells, which means well balanced, so that they can age with a predictable and smooth way. A bad battery fails suddenly. How to find if it's a bad or if it's a good one or a bad one? Well, you can look at the C rating, but it turns out that the C rating is way overrated by most manufacturers. There's no standardized way to measure it. So measuring the internal resistance is probably a better method. And if you search on RC groups, you find that for the lithium polymer chemistry, a baseline figure for a very good cell is expected internal resistance in the order of magnitude of 12,000 divided by the capacity in milliamp hours, and you get milliohms. So if you have a 2,000 milliamp hour battery, you can expect 6 million per cell from a very good battery.
What's the nickel metal hydride equivalent?
I haven't been able to find anything like that, but what I see, if you think that about what Sanyo states for this is 2,000 and it's 25 milliohms, so it's 4 times as large.
Yes.
Yeah. So I think you can. It's more like not 12,000 but 50,000 divided by the capacity.
Yeah.
It's divided by milliamp.
Oh, sorry, milliamp hours. Yeah, I should have stated that. Next one. Of course, a word of caution, especially with LiPo batteries, a short circuit can be very dangerous because we all know LiPo cells would readily swell, split open, and catch fire. Maybe a little bit less so today than in the beginning of the LiPo revolution, but it's still very scary. So care must be taken when doing these measurements. The latest PCB revision, the one that's available on GitHub, has very wide trace spacing for better insulation. Even better, I didn't do it, but you could also consider putting a fuse in series to avoid shorting. It's probably a good idea. And if you decide to build it, be careful and inspect all the solder joints, because especially with multi-stranded wires, it's easy to have a stray strand making a nice short to the neighboring pads. And of course, solder bridges always avoid.
Francesco?
Yep.
Just yesterday. If you don't take your batteries off your charger right, sometimes you you unplug it from your charger before you take it out of your batteries. And
Oh,
I so for just a brief second, they touched.
Yeah.
And I didn't even notice anything, but when I saw it, I jumped and separated them, but I did notice the pack got kind of warm.
Yeah.
So I figured for me, is it a reasonable test to just see if I can charge it and discharge it, charge it and discharge it, see if it,
Yeah, you probably, and if the content was short in time, it's not gonna create, you're not gonna have any problem, especially because it's likely it was balanced, because you use the two.
yeah, I always balance
Red
it.
and black. What happened to me once is that I disconnected the power wires, but not the balancing tap. And the positive terminal contacted for a moment one of the other
One of the cells.
balancing plugs, because I have a board with 6 of them.
Yeah.
And this created a short that was affected only one cell. And so from that moment on, the pack became unbalanced. And balancing it back is tricky.
Okay, but just a quick short would do it to
Yeah.
all the cells, so it's kind of stays in balance a little.
Yeah, it should remain in balance. In
Yeah,
case.
but to test it, you would say charge it, discharge it a few times.
Yeah.
Okay,
3 or 4
or
times.
use your little device.
Or use the phone.
Okay, well, which I
And,
brought it, so.
You were lucky because with the amount of current that the modern batteries can deliver, it's easy to weld the connectors together and to be unable to separate.
Yeah.
Oh. And at that
Yeah.
point, that's where it gets scary.
You have one left.
Yes.
You have a 12,000 milliamp hour battery.
Yeah. And I think this was the last slide, so I think the rest is the demo. We can, unfortunately, I don't have a camera to show it on the
Yeah,
screen.
well,
but we
let's
can-
maybe we should just turn the lights
Right.
together. Huh?
Exactly,